What if I told you there's a material that defies physics? Or, well, at least our common intuition about how things physically behave. I mean, we've all stretched a rubber band, right? Or a piece of plastic. You pull it lengthwise, it gets longer, but what happens to its width?
It gets thinner, it necks down.
Exactly. That's just standard physics.
Yeah.
Now, picture a high-tech fabric, a super felt, let's call it, that you pull in one direction. And instead of getting thinner, it actually gets thicker.
Right. Perpendicular to the pull.
Okay, let's unpack this. We are diving deep into the bizarre and frankly brilliant world of mechanical metamaterials, specifically a fascinating subcategory known as auxetics.
It's a really fascinating area.
The core concept here revolves around a property called the Poisson's ratio. For almost every material you can think of, that ratio is positive. You pull, that's positive tension, and it shrinks sideways.
Negative transverse strain.
Right. But auxetics, they have a negative Poisson's ratio. So when you pull them, they actually expand in at least one transverse direction. It's like a reverse rubber band.
And that counterintuitive response is exactly why these materials are of such huge interest across engineering and design.
Why is that? What's the advantage?
Well, because they get thicker where they're stressed, they redistribute force incredibly efficiently. This offers enhanced performance in some really vital areas. Think composite materials, impact absorption, acoustic dampening.
So if you can make something that gets tougher and denser right at the point where it's hit.
You've completely changed the game. Historically, the most famous example of this was Lake's reentrant foam, where the internal cell walls are carefully collapsed to create this structure. But we also see hints of it in nature.
Oh, really? Where?
In certain types of skin, some ligaments. But the material we're focusing on today, these networked fiber structures like stiff felt, often show what's known as an out-of-plane auxetic response.
And that's the key dimension, isn't it? The increase in thickness when pulled lengthwise.
It is. This specific celt nonwoven provides a scalable, accessible platform to study that exact effect.
So let's jump straight into the material itself. We're talking about a commercially available stiff felt. It's a needle-punched, non-woven fabric made from polyester fibers, PET, and it also includes a low melting point component.
Right, and that low melt component is designed to bond the whole structure together.
The sources describe its structure as being intermediate. It's somewhere between a purely physically entangled, non-woven, where everything's just tangled up like, I don't know, spaghetti, and a solid composite material, where everything's rigidly glued.
And that dual identity is everything. It's what makes it work. On one hand, you have the physical entanglements. These are purposely included needle-punched columns.
What are those, exactly?
Think of them as dense vertical assemblies of aligned fibers that go right through the material's thickness. They're sort of the main engine for thickness recovery later on.
Okay, so that's the physical part. And the glue.
The glue comes from the fused bonds. Because of that low melting point component, when the manufacturer heat compresses it, they create these chemically bonded connections where the fibers touch. That's what gives the felt its initial board-like rigidity.
And this is where we get the first genuinely surprising finding. Unlike a lot of other non-woven studied before, this stiff felt was already auxetic in its as-received state, or AR.
Right, straight out of the factory, before the researchers did anything to it.
It came with this bizarre property already built in.
It's a critical observation because it sort of changes our understanding of how easily you can achieve auxeticity. The hypothesis is that the initial manufacturing step, that heated compression, inadvertently deformed those internal needle-punched columns.
Can you help us visualize that? How does stretching a pre-deformed column make the whole thing get thicker?
Okay, so think of those columns not as perfectly straight, rigid elements. Think of them as slightly bent, microscopic springs that are bowed inward because of that factory compression.
I see.
So when you pull the fabric at its ends, those bent springs, the columns, they try to straighten themselves out. And as they straighten, the only way they can really do that is by pushing the material out transversely. In this case, that means pushing the top and bottom surfaces further apart.
And boom, you get an increase in thickness.
Exactly. That initial processing step created a structural predisposition for auxeticity just by bending the internal framework.
So naturally, the researchers thought, if the factory's compression helped, what if we did it again, but with more control?
Precisely. And that leads to the post-processing treatment they applied to create the treated, or TR, samples.
What did that involve?
They basically put the AR felt through a second, more controlled compression cycle. They applied simultaneous heat, 70 degrees Celsius, and pretty substantial pressure, 2.5 megapascals, and just held it there for 24 hours.
And 70 degrees Celsius isn't a random number, is it?
Not at all. It's highly deliberate. It's right near the glass transition temperature of PED. It allows the polymer chains to relax just enough to reorganize and bond, but not so much that the structure melts or collapses entirely. They essentially engineered a far denser, more tightly controlled fiber network.
And the change in mechanical performance is, well, it's dramatic. It starts with the material's structural permanence.
Yes. What's fascinating is what happened when they let it relax after that intense compression. Compared to similar PET nonwovens or even wool felts, the TR felt showed the lowest thickness recovery.
So it didn't bounce back as much.
Not even close. It only bounced back to about 45% of its original thickness after the pressure was removed. This is a huge indicator that the treatment worked. It created a highly stable, highly bonded, dense structure. They locked the network in place.
And crucially, that locking mechanism translated directly to the property we care about.
It substantially enhanced the auxetic response. You got a much bigger thicken for the same amount of pull. The TR samples had significantly larger magnitudes of thickness strain compared to the AR samples, especially at those lower, more practical strain levels.
And it got tougher, too.
Oh, much stiffer. The TR felts actively resisted being deformed, requiring higher stresses. And the numbers really back this up. At a defined 15% strain, get this, the average load required for the TR sample was 539 newtons.
Okay. And for the original as-received sample?
Only 432 newtons? That's roughly a 25% increase in load capacity. That jump confirms that the thermal treatment created more interfiber entanglement and more of those fused bonds.
That's a huge enhancement. But for any practical application, the question isn't just, can it do this once, but can it keep doing it?
Can it survive repeated stress?
Yeah.
Right, so that brings us to the reversibility and the cyclic loading tests.
What did those show?
A very clear dividing line based on how much you stretched it. At low strains, we're talking 1% and 2%, the material was almost perfectly reversible.
So it behaved elastically.
Exactly. The thickness returned to near original values after unloading. The internal structure, those bent columns, they largely just snapped back into place.
But the moment you push it past that threshold,
Things change permanently.
Oh.
At higher strain levels, 3%, and up the material entered the plastic regime. Permanent changes occurred. After you pulled it and then relaxed the force, the thickness stayed larger than it was originally.
a permanent thickening.
Right, which suggests an accumulation of damage or, more accurately, some kind of irreversible structural reorganization.
And the ultimate failure test at 20% axial strain, that really shows the sacrifice the material makes.
It does. The features responsible for recovery were pretty much compromised. After that initial big pull to 20%, the recovery in the next cycles was minimal. We're talking only about 5% of the original thickness.
So the columns broke.
It strongly suggests that the needle punch columns, the key feature enabling that elastic snapback, were permanently fractured or yielded at that high strain. The enhanced bonds held it all together, but the mechanism for self-restoration was gone.
And related to this breakdown, they observed a phenomenon called stress softening.
That's right, which is very similar to the well-known Mullins effect you see in elastomers.
Can you explain that for us?
Sure. The Mullins effect is that feeling you get when you stretch a rubber band for the very first time. It takes a lot of force. But if you stretch it a second or third time right after, it feels much easier.
I know exactly what you mean.
That reduced stress level as the cycles increase is correlated with irreversible structural rearrangement or damage.
So in this felt, are we saying the fibers are, getting worn out or realigning themselves permanently?
It's a bit of both. It's the physical manifestation of that structural change. At high strains, you are breaking delicate interfiber bonds or permanently changing the geometry of the entanglements and those buckled columns. This explains why the material's reversibility dropped off after multiple pulls. It was finding a new, softer configuration with each destructive cycle.
This whole discussion of stability, elasticity, controlled failure, and this push-pull between entanglement and fused bonds, it all leads to the conceptual aha moment of this research. The connection between the behavior of this simple stiff felt, and the advanced engineering concept of tensegrity.
The Tensegrity connection's a beautiful link.
For those who aren't structural engineers, tensegrity is a mix of tensional integrity. It's a design where compressed elements, like struts or rods, are held inside a continuous network of tensioned elements, like cables. The whole thing is stabilized by press stress.
It's a system where compression and tension are in perfect balance. And this is where the highly structured yet messy reality of this stiff felt maps beautifully onto theoretical models. specifically models of reentrant tensegrity.
Okay, draw that analogy for us.
So micro-CT imaging confirmed the felt had these distorted, rotated fiber columns. These columns which are under compression from the thermal processing.
They're the struts.
They're the struts. They're analogous to the rigid curvilinear cylinders in a tensegrity structure, and the surrounding fibers and those fused bonds which hold it all together.
They're the tensioned cables.
Exactly. The whole messy network is self-stabilizing, held in equilibrium by this balance. The stiff felt is basically a naturally occurring or maybe accidentally manufactured micro-tensegrity system.
But here's the key question for me. Why is the inherent irregularity of a felt a benefit here? I mean, usually we engineer perfect crystalline structures for strength.
That is such a great point. And that small-scale network irregularity is actually key to its robustness.
Yeah.
In a perfectly engineered tensegrity structure, if one element fails, the whole system can just catastrophically collapse.
Right.
But in the irregular entangled felt, that variation allows the material to undergo gradual morphing. It distributes the failure points. That irregularity saves it from immediate collapse, making it resilient where a perfect composite might just fail instantly.
So the messiness is a feature, not a bug.
A critical feature. And if we connect this back to the mechanical data, the fact that the material finds a new, stable, relaxed configuration after high strain, that perfectly supports the idea of the felt acting as a multistable tensegrity structure.
Multistable, meaning it can exist in more than one stable state.
Correct. You put in enough energy, that 20% axial strain, and you activate a conversion to a new network configuration. It's like a complex puzzle clicking into a different, equally stable arrangement. The system restabilizes itself, just in a damaged state.
So the takeaway is that even an imprecise, mass-produced material like stiff felt can functionally behave like a sophisticated designed tensegrity structure.
That's it. The results support the idea that these highly entangled and connected fiber networks can be viewed through the lens of tensegrity, showing that auxeticity and tensegrity can coexist and even reinforce each other.
So what does this all mean for the future? We've established that these non-woven textiles are a powerful, accessible, and scalable platform for making these unique metamaterials.
Well, we're looking at any application that can leverage this thickening and stiffening under stress. It's foundational for high-performance fiber composites. Imagine a bulletproof vest or a helmet liner that gets denser when it's hit.
Wow.
And it's also vital for energy dissipation, superior impact absorption, potentially next-generation acoustic dampening.
And the major achievement here is just how accessible this is. You're getting this effect from a common material using a large-scale manufacturing process, despite its imprecise internal structure.
Exactly. The principles they've learned can be scaled up and applied to much more advanced materials.
We've seen these really compelling similarities between the stiff felt and theoretical tensegrity models. You have the bent columns as compression struts and the bonds as tension cables. So the final provocative thought for you, the listener, to mull over is this. We saw the trade-off. The strength increased, but at high strain, the recovery failed. So what specific performance parameter, something you can measure during that thermal treatment process, could define the precise point when a textile successfully integrates both enhanced auxeticity and the resilience of tensegrity without sacrificing its future reversibility? Think about that crucial balance point.
That's the million-dollar question.
That's it for this deep dive. We hope we've thickened your understanding of these superfelts today.